the ideal gas laws, or sometimes referred to as the ghost of Amadeus Avogadro. We will talk first about the kinetic molecular theory and the physical state, pressure-volume relationship, temperature-volume relationship, mole-volume relationship, put them all together to get the ideal gas laws, and do some calculations. Before we get started, remember Friday, Saturday, Sunday, so that's Easter weekend. Tutorial 1, quiz 1 will come back online in case you need to make up for something that you missed doing in the first half of the course. Sunday at midnight, shut off. Never go up here again. Any questions? All right. We've talked about the kinetic molecular theory before. Basically, it describes the notion that every particle in the universe has an attraction to everything else, and depending on the amount of energy that something has, that defines the physical state of the matter. We said that solids, the particles don't have enough energy to overcome this intermolecular force, so they just kind of sit in the corner. In a liquid, we put more energy in. We still can't overcome the forces all the way, but we have enough energy now to slip and slide all over each other. Finally, in a gas, we have broken free. Particles are free to move, bounce off each other, bounce off the walls, etc. Talking about gas today, has an indefinite shape, just takes on the shape of its container. Lots of space in between gas molecules, so you can compress it or allow it to expand. And they diffuse uniformly and very rapidly throughout the container, so all samples have the same composition. Now we saw these gas particles bouncing around in that little animation. This is another animation. It's actually a calculation defining what's known as gas pressure. This calculation, we've put 500 gas particles in the container. These walls are fixed, but this one floats. Every time a gas particle hits the top here, it pushes up a little bit, called gas pressure. Gas pressure, just due to the atmosphere, is about 50 pounds per square inch. Now, a square inch isn't that big. 15 pounds striking it just from particles hitting it is a lot. We can show that using what's known as the barrel demonstration. Now, this is a burner, the kind that you cook turkeys on. You know, immerse the turkey, burn the gauze, all that stuff. What we're going to do is light it, and then put a 55-gallon drum on top of it. The drum has a little bit of water in it. It'll heat it up. It'll be full of water vapor at that point. Then we're going to cap it off and throw it into a little swimming pool filled with ice. The water will condense. When that happens, the 15 pounds per square inch will not be balanced, and we will get a reaction. Let's watch. So we're going to light it. It's boiling. Close it off. Here's our little baby swimming pool. Let it kind of sit in there for 30 seconds or so. And kaboom. One more time. Really kind of smashes right down. 55-gallon drums are fairly robust. 15 pounds per square inch is a lot. If we didn't have gas on the inside pushing out with the same pressure, we would look just like the drum. Kind of amazing. You measure gas pressure with something called a barometer. Now these are old-fashioned barometers. We have something like this in the lab actually, hanging on the wall. High atmospheric pressure tends to be associated with good weather, rainstorms, or low pressure. This is just a recording version of the same thing. Little bellows here that goes up and down and makes a line. This guy is called a manometer. It has mercury in this little arm. You put it onto a vacuum line, that's like you would use in lab. Suck down your vacuum. What it does, it pulls the two mercury levels so they are equal. The distance between them gives you the pressure. Don't use things like this anymore. Today it's all digital. Hook it all up, and away it goes. My favorite, however, is this guy, because when I was a child, we had one. Now, I grew up in Florida in the 50s. In those days, there were no such things as satellites, which means that if a big hurricane was coming, you really didn't know until it was there. So you had one of these guys sitting on a shelf. This is sealed. This is open to the air. As the atmospheric pressure changes, this little level will go up and down and up and down. If a big storm is coming, it's associated with low pressure, the water will come up, squirts out the top, and you know it's time to go somewhere else. Yep, that's the way it used to be. Those were fun days. All right, the classic lab barometer looks like this. This is a long glass tube. It's filled with mercury. Now, this is a little beaker down here. It's also filled with mercury. The way that you prepare one of these, this used to be a standard experiment in general chemistry. You would take your tube, very carefully pour mercury down the tube, fill it up, put your thumb over it, turn it upside down in the beaker, and let go. The weight of the mercury pulls a vacuum on top. At sea level, the distance between this level and that level is 760 millimeters. That is deemed atmospheric pressure. Now today, of course, we can't do that because mercury is toxic these days. I guess it didn't used to be, but today, if you want to measure atmospheric pressure, this is what you use. Again, it's all digital. Any questions? Well, the units that we use to measure gas pressure, 760 millimeters of mercury, that is the height here, is defined as 1 atmosphere. Now, this 1 and 760, exactly 760, are defined as exact numbers. So these are not included in significant figures. If it's 761, then it is. 1.001, it is. But these two are exact numbers. Sometimes millimeters of mercury are referred to as torr, T-O-R-R, The two are identical. I have no idea why you would use that. Millimeters of mercury is so simple. Atmospheric pressure, we said that could be 14.7 pounds per square inch. We will never use inches. We will only use either atmospheres or millimeters. If you have a pressure given in atmospheres and you want millimeters, the magic number is 760. Simply multiply atmospheres by 760 to get millimeters, divide to get atmospheres. 760 is your magic number. Now our first gas law is the pressure-volume relationship. We said that we could compress and expand gases because there's so much space in between particles. The relationship describing that is Boyle's law. Boyle's law says the volume occupied by a fixed quantity of gas is inversely proportional to the pressure. Okay, this is a little device that you can use to demonstrate that. As a platform up top, this is a captive gas and a meter. If we start off with a very small pressure on top, well, I didn't even see the needle move at all, right? But if we put a more substantial pressure or more substantial weight on this, then it compresses and the pressure goes up. Volume goes down as pressure goes up. That's an inverse relationship. Now, anvils are fun, but we can do this more systematically if we have a device up here that slowly will increase the pressure, and we can record pressure and volume. So we do that. As the pressure goes up, the volume goes down. But you'll note that this is not a straight line, is it? It's a curve. If you think about it, it has to be a curve because the volume has to be asymptotic to zero. It's never exactly zero because the gas itself has a volume, so it has to go on a curve. The curve turns out to be a hyperbola. Now, beautiful hyperbola, volume versus pressure. But scientists, chemists, not mathematicians, but chemists don't like curved lines. We really like nice, clean, straight lines. But mathematicians tell us that if we have a hyperbolic relationship, you can convert the curve into a straight line simply by taking the reciprocal of one of the axes. So this is 1 over pressure versus volume, beautiful straight line down through the origin. Mathematically, we can say that this tells us that volume is inversely proportional, that's 1 over, the pressure. We can write it like this. The little alpha sign here is actually a proportionality sign. Volume directly proportional to 1 over P. Now, anytime you have a proportionality sign, you can change that mathematically into an equal sign and a constant. The constant is actually the slope of this curve, but now it's an exact relationship. Anytime you have proportionality, you can substitute equal and change. So, let's take this equation and let's isolate K. K is equal to pressure multiplied by volume. What this tells us in words is that pressure times volume in any system is a constant. So we had two systems we looked at. All very weight, virtually no change in pressure, and a envelope, big change. Over here, the initial state is going to be P1 V1, and it's going to be equal to a constant. Over here, this is our final state. We'll call that P2 V2, and it's equal to a constant. Now, this is exactly the same apparatus. It's the same gas, the same meter, everything. That means that this constant and that constant are the same. If they're both equal to the same thing, they are equal to each other. P1 V1, P2 V2. This is what is known as Boyle's law. This is what's known as Robert Boyle. Kind of an arrogant Englishman. I don't think I like him. Any questions? All right, then let's just do a simple problem. We have 12.5 liters of gas. We're at 0.82 atmospheres. We're going to change our pressure to 1.32 atmospheres. And we're looking for the final volume. Boyle tells us P1 V1, P2 V2. I'm going to take this equation and solve for V2 in terms of the others. V2 is over here, so V2 is going to be P1 V1 over P2. Simply substitute. Atmospheres will cancel. And do a simple math. 0.82 times 12.5 divided by 1.32. We're at 7.8 liters. Pressure went up. Volume went down. Pretty simple, right? Let's do another. Here we have 150 mils of CO2. We're at 35 milliliters of mercury. We're going to decrease our volume to 50. What's the final pressure? Well, once again, it's a Boyle law problem. P1 V1, P2 V2, and we're going to solve for P2. P2 is going to be equal to P1 V1 divided by V2. Both of these are in milliliters. That's fine because it will cancel. And our pressure result will be in terms of millimeters of mercury. Substitute in, cancel milliliters. 35 times 150 divided by 50, 106 millimeters. Now, what if I were me and said, give me this in atmospheres? What would you do? 760 is our magic number, isn't it? If we have millimeters, want to go to atmospheres, simply divide by 760. We're at 0.14 atmospheres. Any questions? All right, the first tutorial for the chapter by George is called Boyle's Law. Here we have a gas system, initial pressure of 5 atmospheres. We have 50-50 mils. The volume's going to change to 5.62 liters, so we have to adjust these so they're the same unit. And we're looking for the resultant pressure in atmosphere. We're starting off in atmosphere, so that'll be automatic. The way I suggest doing these is just to make a little table, a little list of what you've got and what you're looking for. So P1 is going to be a 5.05 atmospheres. We either have to change this to liters or this to milliliters. Doesn't matter which one, I change this one. We're looking for P2 in atmospheres. So we're good. Going to rearrange our Boyle's law. P1 V1 equals P2 V2. P2 is P1 V1 over V2. Do our substitution. Milliliters cancel. We're at 4.5 atmospheres. Let's do one more. Here we're at an initial pressure of 2350 millimeters. Our volume is in milliliters. We want the volume in liters. And our pressure is changed from 2350 to 5.6 atmospheres. So a couple things we have to get uniform. Again, we'll make a list. Change this simply by dividing by 1,000. We have the pressure in atmospheres. How do we get millimeters? Multiply by 760. And we're looking for our volume in liters. So that works. All right. We simply take P1, V1, solve for V2, substitute, millimeters of mercury cancel, and we're at roughly 3.6 liters. Boyle's law is fairly straightforward. Really, all you have to do is make sure you remember the relationship, solve for the unknown, and you're done. Any questions? This tutorial is also notorious because it has a coding error in somewhere. I can't find it to save me. And sometimes you get a problem that's nonsense. If you do, just hit no problem. Okay? I really work hard on it. I can't find it. But temperature volume relationship. The general nature is going to be shown in our animation here. We have a balloon. We are going to pour liquid nitrogen all over this balloon. That will cool it. Liquid nitrogen is minus 196 degrees centigrade. Very cold. Fun to play with. So let's take our poor balloon and let's do this. The balloon knows what's going to happen. It's getting nervous. And here it goes. Liquid nitrogen everywhere. As it cools, the balloon gets very, very small. Now, as the liquid nitrogen evaporates, the gas inside the balloon warms. As it does, our volume increases. The simple notion here is, as temperature decreases, so does volume. Temperature increase, so does volume. Looks like a simple linear relationship. Well, balloons are fun to play with, and so is liquid nitrogen. But in science, sometimes we do real experiments and plot things out. Let's go ahead and look at the volume of a sample of gas as we change our temperature. We are going to start off with 0.25 moles of a gas, drop the temp from 200 to minus 200. Measure the volume along the way. As we predict, as the temperature decreases, the volume decreases. You never just stop with one. Let's do it again with half a mole. Same trend. Temperature decreases, volume decreases. One more time. Temperature decreases, volume decreases. Not only that, but if you look at these lines and mentally extrapolate them, they all look like they're heading towards the same spot. In fact, they are. This is minus 273.15 centigrade. This forms the 0 point of a new temperature scale that we'll call Kelvin. This 0 point is also what's referred to as absolute zero. You can never actually cool something all the way to absolute zero because its volume would then be zero, and nothing has a zero volume. So you can get very, very close, but you can never quite get there. Whenever you do a gas law problem, you must start at zero and you must use the Kelvin scale. Now, this is what we saw in our animation. The volume was directly proportional to temperature. Temperature went down, so did volume, whatever. Let's take proportionality, make it a kT, and then let's isolate our K. K is volume divided by temperature. Now we had two states. We had a very cold V1, T1, and then as the nitrogen evaporated and it warmed, we went to V2, T2, fully inflated. This relationship is called Charles's law. Once again, same balloon, same gas, this K and that K are the same. So we could write V1 over T1, V2 over T2. That mathematically is Charles's law. Now Charles, unlike Robert Boyle, kind of a nice, ruddy-looking guy, Frenchman. Jacques Charles is his name, actually. First time I saw this picture, now I'm a little older too, but I'm not sure anybody even knows this guy anymore, but I thought, looks very familiar. Anyway, Charles was a very interesting sort of guy. He was a balloonist. He and one of his workers were the first people to ever fly in a balloon. In France, they flew up, went over the French countryside, and then landed. Now, the balloon that they used was filled with hydrogen gas. They made it by taking iron, reacting it with sulfuric acid, single replacement reaction. They got hydrogen and iron to sulfur. So, turned out that this was a big event in France around 1790. They did the launch actually in the area of Paris, where the Eiffel Tower is today. And they charged people just to come and watch. Benjamin Franklin was actually there to watch. So they added iron sulfuric acid. This reaction gets very, very hot. Very hot. The gas coming out was hot. It went in the balloon, puffed it up nicely, and then just like our little balloon, cooled down and balloon collapsed. So they did this again, balloon up, balloon down, balloon up, down. Kind of embarrassing after a while. This is probably where Charles got the idea for Charles's Law. Okay. Anyway, they finally got it full. Like I said, he and a co-worker took a couple bottles of wine, crawled in the gondola, and took off across the French countryside. Now they were about a quarter mile up. The wind blew them away from Paris. They decided it was time to come home. Well, they looked down, and by George, down there was a little village. Let's land by the village. They'll be so happy to see us. We can get a free ride home, whatever. Well, the peasants in the French countryside were not used to seeing balloons, especially balloons with people in them. And so as they saw this thing starting to descend on their village, they reacted the way French peasants would. They attacked it with pitchforks, knives, dogs, stones. This one even has a gun. Yeah. Fortunately, they didn't do the other thing that they did in Beauty and the Beast, and that is carry torches, because the hydrogen would have exploded, wouldn't it? That would have been a real disaster. Fortunately, Charles lived through this, but he never rode in the balloon again. It was traumatic enough. Hydrogen gas, it turns out, is the perfect gas for balloons. It's very abundant, easy to make, whatever. Around the 30s, it became very popular as a buoyant for huge dirigibles. So this is German. It's the Hindenburg. It's a massive airship. It was designed for cross-Atlantic travel. So it was going to leave Berlin, fly across the ocean, land in New Jersey. Well, they flew it around Europe for a while, and it worked fine. So they tried to cross it. Crossing worked great. They went all the way across. The time of it was much less than the ship. It was a great thing. But unfortunately, the skin here is aluminum. And there was a thunderstorm in New Jersey. What they theorized happened is that the charge in the clouds was transferred to the skin. So it was now very charged. As they vented the hydrogen gas to come in for a landing, there was a spark. And kaboom. This was the end of hydrogen-inflated balloons. It's a shame. That's why we use helium now. But we're out of helium. Helium is not easy to get or make. Hydrogen is. It's a great problem if you want a floating balloon. Any questions? All right, back to Kelvin. We said that water freezes at 0 centigrade, boils at 100. In Kelvin, this is 273 Kelvin, 373 for the boiling point. Again, it's 100 little degrees at the extreme. That means conversion between centigrade and Kelvin is simple. It's always a factor of 273 degrees. The size of the degree is identical. Whenever you do a gas law problem, once again, you must use Kelvin as your temperature scale. Let's just do a couple very quick conversions. 1,000 minus 150 is 100. Remember, Kelvin, centigrade, plus 273. That means that centigrade is always less than Kelvin. Kelvin is always bigger. So we're going to add 273 here. Add it to our negative number. We're at 123. And again, water boils at 373. Kelvin is always bigger. All right, typical Charles's law problem. We have 50 mils of gas. We're at 26.4 centigrade. We're going to heat this until the volume is 62 mils. What's our final temperature? This clearly is a Charles's law problem. We will take the mathematical equation, solve it in terms of T1. I'm sorry, let's just say T2, shouldn't I? Solve it in terms of T2. Get rid of that. T2 is what we want. T2 is V2 T1 over V1. Now, V2, that's our final volume, 62 and it's milliliters. V1, our initial volume, 50, and again it's milliliters. Temperature here is given as centigrade. We need to fix that. So we take this, add 273, we're roughly 300 Kelvin. So let's take it, substitute in. Milliliters are going to cancel. 62 times 300 divided by 50. We're at 373 Kelvin. We're dealing with three significant figures, so let's round this to 374. Now, if I asked you what this is in centigrade, what would you do? Simply subtract 273. Or 101 centigrade. Well, Charles also has a tutorial, but this one works. We have a gas system here, initial volume and tempo, 11,000 mils. Again, we're in centigrade here. We're changing to 7.6 liters, and of course we want our temperature in centigrade. Make a list of what you got. We're defining that as V1. We will take 106, add 273. Change our volume in liters to milliliters. They cancel it, doesn't matter. And we're looking for T2. Again, T2 is going to be V2 T1 over V1. Substitute in. Milliliters will cancel. We're 264 Kelvin. Fairly straightforward. Just make sure you're always in Kelvin, not centigrade, and that your other units all match. Any questions? All right. Well, remember when we did this? I'll be honest with you, doing an experiment, doing it right, is a lot of work. So once you have a set of data like this, you kind of look at it and say, can we get anything else out of this? We've already got an absolute zero. We confirmed the linear relationship. But what if we were to hold our temperature constant and simply change the number of moles? So we're just looking at these data. Constant temperature, different number of moles. That is the mole volume relationship. Our third gas law. Basically what it says is that as you increase the number of moles, the volume goes up. This is Avogadro's law. So, very straightforward. Again, a simple linear relationship. We have an inverse relationship with volume, a direct relationship with temperature, and a direct relationship with number of moles. We can write it like this. That's Boyle's law, Charles's, and Avogadro's. Volume is directly proportional to all of these things. Well, I contend that if volume is proportional to each of these individually, that you can take and wrap them all together and say volume is proportional to NT over P. Let's change our proportionality symbol. But you know what? We've used K before, used it way too much. Instead of K, I'm going to use a different letter. I'm going to use an uppercase R, and I'm going to call it the universal gas constant. So we have V equals RNT over P. Well, that's a fine equation, but it's not a fun equation. If you take both sides and multiply by P, you get PV equals nRT. It's an internal line, isn't it? It's fun to say. PV equals nRT. This is our ideal gas law. If we know any of these guys, we can solve for the others. Kind of neat. And it would be neat if we knew what R was. R is a constant, remember? But what is it? Fortunately, Avogadro explained to us how we could do that. Remember, experimentally, 1 mole in a gas at 273 Kelvin, 1 atmosphere, has a volume of 22.4 liters. Let's take and solve for R. R is PV over NT. Well, pressure, 1 atmosphere, volume, 22.4 liters, in 1 mole, temperature, 273. One atmosphere, 22.4 liters, 1 mole, through 273 Kelvin. Now, typically at this point, red X's would appear and things would cancel, right? Nothing cancels. Not only that, when you solve this, you get a strange number. The number is 0.082057, and the units are liter atmosphere per mole per Kelvin. I can never remember this, even when I could remember things. If you ever need R, on an exam or quiz or whatever, I will give it to you. Okay? If you want to back me up, you can write it on your card too, but you don't have to. It'll be there. All right, so we know what R is. We're looking for the number of moles of argon gas that we have. We have 18.6 liters. We're at 293 Kelvin. Pressure 2.3 atmospheres. PV equals nRT is our ideal gas law. N, the number of moles we have, is simply going to be PV over RT. So, we substitute pressure 2.3 atmospheres, volume 18.6 liters, R 0.082, and finally temperature 293 Kelvin. Atmospheres will cancel, liters will cancel, Kelvin and per Kelvin cancel. This is per mole in the denominator, so it comes up as mole. Simply do the math. 2.35 times 18 divided by 0.08, multiplied by, or divided again by 293, we have 1.81 moles. Only thing you have to be careful of whenever you use PV equals nRT is make sure volume is in liters, pressure in atmospheres. And of course, there is a tutorial, and it's entitled PV equals nRT. It's also called the ideal gas law. Gas system has volume, moles, and temperature. There's our volume, there's our moles, there's our temperature. What's the pressure in atmospheres? Very simple. Make a list. Looking for pressure, we have volume, we have moles, we have temperature, we know PV is going to be nRT. Pressure nRT over V, substitute, solve, 1.86 atmospheres. Now what if on an exam I said, do this, but give me the pressure in millimeters? You would multiply by 760. Any questions? Let's do one more because it's fun. We have a gas system with pressure, volume, and moles of 1.6 roughly, 357 mils, and 0.7 moles. What's the temperature in Kelvin? Right away we remember this has to be liters. So we're going to divide it by 1,000 and get 8.3 liters. PV equals nRT. T is PV over nR. There's our numbers. Do a simple calculation. We're at 223 Kelvin. 225 Kelvin. Now, if we wanted that in terms of centigrade, what would we do? We would subtract 273. Any questions? All right. Time for old exam question. This one, of course, comes with a story. Again, I was writing an exam, and I wanted a question that everybody would get right, just to make them and me feel good, right? So, Which of these corresponds to Boyle's law? Okay. Well, by George, A, V1, V1, V2, V2, that's what we call Boyle's law, isn't it? That's simple. But where did we get Boyle's law from? Our first step was when we realized that TV was a constant. Finally, if you take this equation, multiply it by P2, then by V1, by George, you get this. So all of these are correct, aren't they? And virtually nobody got it right in the class for 500 people. Yeah. So in the next exam, maybe the final, like with Charles's law, same sort of question. T1, V1, T2, V2. Nope. That sounds a whole lot like Boyle's law, doesn't it? That's not right. Or V1 over T1, V2 over T2. So that's one. TV wasn't a constant. V over T was a constant. So that's wrong. There is no way to take this equation and manipulate it and massage it and get that out of it. It's wrong. None of the above is correct. And again, almost everybody does it. Sometimes I still put it on an exam in different forms. So just make sure you get it. More traditional question here. We have 450 mils of gas at 1 atmosphere. We reduce the volume till we get 5 atmospheres. That's our final volume. Well, volume and pressure, this is a Boyle's law problem, isn't it? So we're P1, V1, P2, V2. We are looking for the final volume, that's V2. Going to be P1, V1 over V2. Atmospheres will cancel. Do our math. We're at 90. Here's another one that was supposed to be very easy. Lots of words, but what is true for centigrade and Kelvin? Kelvin is a larger temperature change. No, we said they were exactly the same. Centigrade and Kelvin are never numerically equal. Well, no, they're not. They're always differ by 273, don't they? Only readings in centigrade can be converted to Fahrenheit. Well, that's stupid. Yeah, it's stupid. So, wrapping up the gas laws then. The kinetic molecular theory tells us that gases are in constant motion and it's random. Gas particles collide with the container walls, giving rise to gas pressure. There are no attractive or repulsive forces. All collisions are fully elastic. This is not true. It's not true at very high pressures. Very high pressures that kind of stick. But you got to get way up there. The volume of molecules is negligible. Yep, they're really small. Now, we can wind up all of the gas laws here and summarize it with 3 little videos spoken by a female, so it sounds official.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
If we double the number of particles, we double our pressure. Direct relationship.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
You're going to hit the wall harder and more often. Temperature goes up, pressure goes up. Finally,
if the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
if our volume goes down, our pressure goes up. Boils up. Any questions? Gas laws are really pretty simple, aren't they? Now, there's another form of ideal gas laws that involve much more math, where you deal with an initial system and a final system. We don't do those in 110 because it's just the same calculation except it's cumbersome. So you can wait and do cumbersome in general chemistry. This is our list of tutorials. We've added Boyle's, Charles, and PV equals NRT. Chapter 11, we will add one more tutorial, otherwise we're done. Remember, Amnesty Weekend. This weekend, Quiz 1, Tutorials 1 will be live. They go offline at midnight Eastern Time. 11:59 actually. You shouldn't be up that late anymore. And finally, Wednesday we are doing Lab 9, hopefully. It's decomposition of sodium hydrogen carbonate. Hopefully they will have sodium bicarbonate out on the table. So we will have to see. Any questions? Again, there's the tutorials. Please do them. Thank you and have a good day.